Alright, hello, and welcome to another episode of My 2 Cent. As always, my name is Paul Emerson, and this episode is going to be about force of attraction and how it applies to our observation of gravitation, because there's a lot of information going around that gravity is a push. That gravity is a pull. I was correct the first time. The gravity is a push when in fact gravity is a pull. So what I want to do is I want to address why gravity is a pull, why gravity is not a push. So I'm going to be filming this a little bit differently. I'm not going to be filming myself speaking because science is about observation. So I'm going to start showing exactly why gravity is not a push. We're going to do this by using magnets again. I have two different sets of magnets this time. I know that magnetism is not gravitation. I understand that, but the behavior that you can observe is scientific. Observation is the fundamental principle of science. Without observation, there really is no science, so we can start there. What I want to start with, to get started with this, is I want to start with orientation, because we live in a geometric universe. There is a such thing as space because we experience space, but relativity says that space-time is physical, and that's not true. The physical aspect of space that they describe is only mathematical. It's basically based on mathematical principles and mathematical formulas that accurately describe the behavior that we observe. So the problem with that is that because the math shows us that there is a behavior that can be, because the math can show the behavior that we observe, we say that the math is stating that there is a physical component to the material aspect of space, but there's not. Space in itself is actually nothingness. I know that's hard to believe and hard to understand, but that's the truth. The reality is that when it comes to geometry of our universe, there is no actual space. All of the particles and everything holds all of the energy inside of them. And I'm going to illustrate this like this. We're going to say that this is a particle. Inside of this particle there is an electromagnetic force. There is a gravitational force, there is a strong nuclear force, there is a weak nuclear force, there is an inertial force, there is also a force for motion, there is a force for rotation, there is a force for it to remember its location. All of these forces exist inside of the particle. All of these forces interact with each other. M, L, and R. So gravitational force interacts with gravitational force. Electromagnetic forces interact with electromagnetic forces. Strong nuclear forces interact with strong nuclear forces. Weak nuclear forces interact with weak nuclear forces. They do this through our geometry. And that's one of the things that relativity describes. See, if you have two particles, particle A and particle B, and these particles have location and orientation because relativity is about observation. So you have this particle A at location A, and then you have particle B at location B. Sorry, I'm doing this off the top of my head, spur of the moment, so it may be a little confusing, but as I get better at this, my video presentations will get better. I like to do things more naturally and less planned out because I feel that it really conveys the information better, because I am limited and I can make mistakes. When you see my mistakes, you can learn through my mistakes as an actual added bonus to the learning process. So we have location A and location B. We have particle at location A, we have particle at location B. There's three locations in our space. There's an X coordinate, there's a Y coordinate, and there's a Z coordinate. There's an X coordinate, there's a Y coordinate, and there's a Z coordinate. These particles in our existence are located at these locations. So what you see on this sheet of paper is just two dimensions. If you know anything about the Cartesian plane, you have, I believe it's the y-axis and the x-axis. So the paper itself can be viewed the same way. This is the y-axis, this is the x-axis. So you're seeing the actual geometry. If I had a ruler, I don't, sorry. You can clearly see how these objects have a distance between them. The distance between them is how you know that they have location. That's how you know that they're taking up space. Matter, this is object C, cannot occupy the same space. So this is how math works. I can draw a particle. I can say this particle is located at coordinate 0, x, coordinate y, 0, and coordinate z, 0 on a Cartesian plane. Okay? I can draw another particle here. Now you can clearly see that the geometry between these two particles is different on the paper, but the math can tell you that this particle is also located at coordinate x, this particle is also located at coordinate y, and this particle is also located at coordinate z. I can show you this behavior with the math. The math is telling you that the location of these two particles is in the same exact location. But we know that matter cannot occupy the same space. So two particles of matter cannot occupy the same location. That means that only one particle of matter can be located at one space at one time. Now, because objects are in motion at any given moment in time, which is what relativity describes as the fourth dimension, is time, a particle can be located at coordinate x, 0, coordinate y, 0, and coordinate z, 0 at any moment in time. And then it can move to a new location, and another particle, particle B, can occupy that location at a different time. So that's how we have motion and orientation. That's what is important about space-time and relativity and understanding the behaviors and the interactions. Gravitation acts through space, but doesn't act on space. Electromagnetism acts through space, but doesn't act on space. There is no space. There's only the indirect observation that comes from understanding the behavior of matter itself. When you look at yourself and you look at an individual next to you, you see each other through space. But that doesn't make space actually relative. Space itself is not anything more than an abstract axiom. It has no material aspect to it. There is no physical aspect to space. And that is what I'm trying to address before I can get into the force of attraction. Because we have to understand that aspect first before we can even address how gravity is a pull and not a push. So what we're going to do. I'm going to show you orientation. Orientation is important because you can't accurately describe or understand gravitational interactions or influences if you do not understand orientation. The biggest problem that people have with believing that gravity is a pull instead of a push is that they lack a fundamental understanding in orientation. This is going to be a body of mass, and it's going to carry a mass attraction. The reason why it's carrying a mass attraction and not a gravitational attraction, the reason why matter is described as having a mass attraction and not being influenced by gravity directly is because scientists were smart enough to know that matter doesn't 100% necessarily have to be influenced by gravitation. Even though that is what we observe, that does not necessarily have to be to the absolute truth in the universe, because our observation of the universe is limited to our location on Earth. So scientists were wise enough to know that claiming that matter was gravitational was basically, we say that matter has mass attraction and mass attraction is gravitation. The reason why we say that is because we don't want to say that matter has gravitational attraction. We don't want matter to be limited to being a gravitational influence. See, a subatomic particle has a mass attraction and an electromagnetic attraction. A neutron has no electromagnetic attraction. It has no electromagnetic influence, but it has a mass influence. A photon is described as not having a mass attraction, but it has a gravitational influence. And see, this is where the actual observation gets in the way, because when you start describing things on paper and start explaining the behaviors that you see, you get confused with what is said by what is factual. And you have to make sure that your understandings line up with what you actually observe. So when you're talking about gravitation as a push, what you're saying is this mass will influence this mass as a push. This would describe a push, because the force of attraction itself is going to be in the direction away from the source, which is the center of the mass. So this object will move in a direction away from the mass. I think the reason why people draw the conclusion that gravitation is a push is because we can observe pushes easily. It's very easy for me as an individual to push an object. It's very easy for me as an individual to grab and pull an object, and I can understand the orientation. The problem is that when it comes to interactions, force interactions, you can't see them. See, it's the same exact illustration as the paper. You can clearly see that the magnet is being pushed by the influence. But here's the problem. While you can clearly see the magnets are being pushed by the influence, it takes a very abstract thinking process to not recognize that what you just experienced is a pool. That is what a pool looks like. Can I describe the mechanism that creates a pool? No, I cannot. But what I can do is I can clearly show you an observable pool scientifically. If you can't see this, I mean, how do you see the push? That's a push. This is a pull. So you're asking yourself, Paul, how do you know that what you're seeing is a pull? How do you know that you're not viewing a push? The reason why I know what I'm saying is a pull is because of orientation. It's all about orientation. Right now, these magnets are orientated. If you notice that the magnets push away from each other, it's dependent on the orientation of the magnet. Because this particular type of magnet has a cut. It has been manufactured in such a way that it creates a particular influence based on its actual orientation. Because the electromagnetic fields line up in the universe. Whatever generates the electromagnetic field inside of the matter itself has an orientation that is aligned to the object. And that is why orientation is important. Because as long as this magnet, because they're circles, as long as they're in this particular orientation, then it will always push. They will always push against each other. So what I'm going to do to help you understand what's going on is I'm going to give this some coordinates. Okay. I'm going to give this thing some coordinates. So toward and away from the camera is going to be the z-axis. Basically, from here to here, because we live in 3 dimensions, this is the z-axis, right? So this is the x-axis, and this is the y-axis. Now, I'm going to show you something very interesting when it comes to magnets and attraction that a lot of people don't ever truly understand because they don't actually sit down and play with magnets. Okay, let me make sure that they're aligned correctly. Okay, we got to push. And again, this is the z-axis. Now, my magnets are going to repel each other, right? I'm going to rotate this magnet 180 degrees on the x-axis. This is why quantum physics describes force interaction, the charges, as clockwise and counterclockwise. See, you don't recognize this if you don't play with the magnets. If you just listen to what is being said and you don't really put any energy into looking at the actual observations in nature, you miss this kind of stuff. I just rotated this magnet 180 degrees. It's not going to push. It's going to pull. It's going to pull. If I rotate it back 180 degrees, it's going to push. The orientation is very important. This is the reason why Newton's law of gravitational attraction, I can't quote it accurately, is defined as creating a force from the center, as if the masses are at the center. The mass attraction comes from the very center. The reason why the mass attraction comes from the center is because gravitation is not influenced by orientation. Magnetism, when it comes to gravitation, we observe a uniform, indiscriminate mass attraction. That means that no matter how many directions are changed, you change the orientation of an object, it will always create a pull, not a push. The magnets, I can illustrate attraction with the magnets as a pull because of the dualistic nature of electromagnetism. But if these magnets were mass attraction, as they got close to each other, they would attract only. If I rotated this magnet 180 degrees, and it was mass attraction, when I moved this magnet toward this other magnet, because it would be operating under gravitational forces, it would pull toward the other magnet. But it doesn't, because gravitation is indiscriminate mass attraction. I can illustrate gravity very easily for you by simply dropping the magnet. I can do this experiment over and over again until I'm 100 years old. And I promise you that every time I drop a magnet, it will always move toward the center of the earth. Because as I said, from the camera to the table is gravitation. It's the z-axis. If I take a magnet, this magnet from above, I can still generate a z-axis attraction or repulsion because we live in 3-dimensional geometry. I just reversed the field, and if I did this correctly, the magnet should repel because it's going to operate on the actual, it's going to operate on its behavior. It will always do that 100% of the times, all the time. This is observation. I cannot say that these magnets will not repel. I cannot say that these magnets will not attract because they're not going to listen to what I have to say. They're going to behave the way that nature describes them. And that is why gravitation is a that is the reason why gravitation is a push and not a pull. So I'm going to show you how gravity works using illustrations. That's the reason why I had a paper, because I can show you the forces. You can ignore the theoretical illustrations, but you have to remember that the illustrations that I'm about to show you are influenced by the observation of electromagnetism. Because just like we can see that a magnet can both attract and repel, we always see that gravitation pulls toward the center of the earth. Always, 100% of the time. You can change the mentality of it in your own mind and change the orientation so that that's not the case, but that's always the case. And this is basically how it works. The earth, this is Earth, has a gravitational attraction that goes out in all directions. This gravitational attraction pulls everything toward the planet. Everything that has mass is pulled toward the planet. The sun has gravitational attraction. All of the bodies in the solar system are pulled toward the sun. This is how it works. So, what happens is, there's two basic forces in our universe. There is, to use these again to illustrate this, there is a motion that is rectilinear, basically a straight line motion, and then there is a motion that is curvilinear. There's a rectilinear motion and a curvilinear motion. That's pretty much how it works. The same force of attraction that is operating on this magnet, that causes this magnet to spin around this other magnet because of the geometry, circular geometry, is the same reason why the moon orbits the earth. Because the force that I'm generating is a rectilinear force. It's a rectilinear force. The force that I'm exerting on this magnet is rectilinear. But the influence of the electromagnetic attraction creates centrifugal force. You notice the first thing you see is centrifugal force. Why is the moon orbiting Earth? Centrifugal force. The indiscriminate mass attraction of the Earth and the indiscriminate mass attraction of the planet causes a spin. The Earth is at the center because the mass is greater, and the moon is orbiting the Earth because its mass is lesser. The moon is actually trying to move away from the Earth, but it can't. This is what Newton outlined. Newton's law of universal gravity has outlined this. Newton described the behavior of the movements of the celestial bodies in the universe, and as well as the movement and the behavior of the quantum. He did this by observation, not by sitting down doing mathematics. He was a great mathematician, but he was more concerned with what he was observing opposed to what the numbers on papers was showing him. He made sure that he took time out to make sure that the math matched the observation. Relativity and quantum mechanics, they're so busy looking at the numbers now that they're ignoring the observation, because what they are observing doesn't even comply to observation. You cannot directly observe the quantum because it's too small. So they're putting as much faith, they're putting 100% faith in the math, but they know for a fact that math is not observation. So gravity is a push. That is what we believe. I can clearly show you with these magnets that, in fact, gravity is a pull. If gravity was a push, this is the behavior that you would expect to see. Notice how it vectors away. How is the sun orbiting the Earth if the orbit is vectoring away from the center of the attraction? Because the field strength from these magnets comes from the center. It works its way outward. Inversely, that means that as the distance between them is reduced, the distance between them determines the field strength. The further these magnets are, the electromagnetic interaction between them is dropping. The further I move them apart, the more it drops. The closer I bring them together, the stronger the field gets. The stronger, the stronger, the stronger. Right now, they're actually pulling on each other. The only reason why they're not touching is because of the opposition of my hands. The force of my fingers is greater than the force of their pull. So there's a strong field between these two magnets that you cannot observe. But I can observe it because I can feel it. My ability to feel is one of my observable senses. So I can clearly feel the strength of these fields. Just like if I flip this over 180 degrees, I can feel the push. I can feel these two magnets pushing off each other. If I flip it again, I can feel them pulling on each other. If I let go, you can see it. This is what we're observing. This is how gravitation is being. This is basically the closest thing to understanding gravity that you're going to be able to get with the material aspects of our universe. You can argue all day that electromagnetism is not gravity, but what you can't argue is that force of attraction that you observe and electromagnetism is not somehow the same abiding laws of force of attraction that will apply to gravitation as you see it. Just like that magnet will literally fly through the air. In opposition to gravitation. That in itself says a lot, that the magnet will not even fall. It will just go straight to the electromagnetic attraction. The reason why is because the electromagnetic attraction and gravitational attraction are different. That's why gravity is described as mass attraction, because the gravitation that is acting on this magnet and this magnet is constant. So the magnet fell, but it moved on the y-axis faster than it moved on the z-axis. So it attached to the magnet that has been supported by my hand, which has been supported by my body, which has been supported by the surface of the ground or the surface of the earth. And that's what you're seeing. It's as clear as I can get. It's pretty self-evident. The behaviors are there. So I'm sorry that I can't give you a mechanism to explain how gravity works. I'm sorry that I cannot give you a mechanism to describe exactly how the force of attraction works. But what I can do is I can show you clearly the force of attraction and the force of repulsion. And if you are a scientist, or if you want to inspire to be a scientist, and if you want to be inspired to have a scientific method of thinking and analyzing and understanding using logic and reasoning and observation, then you have to accept what nature shows you. I could do a parlor trick. I could do some trickery, and I could distort the information in some way to coerce you into believing that what you're seeing is true. But that would be a lie, and I haven't done that. I'm not trying to mislead you in any way. I'm showing you exactly what nature is showing me. The only thing that I would hope is that you would accept the information, because before you can understand, all knowledge is built upon a foundation of itself. Every principle builds on top of itself. That's the reason why one principle stands on the other principle. That's where ego comes in, because if you have a false value and you build another value on top of that false value, once you change this false value, this false value will influence this value, and you have to restructure your thinking. And it creates an uncomfortable position in your mind, because I don't want to go into that, but you just have to be able to accept what you see and observe it. And you have to use science to be able to truly accept what you see and truly be able to recognize and accept your observations of your universe, because you are a living being in your universe. It's pretty much, I don't know how else to put it now. This is probably getting pretty drawn out, so I think I'm gonna just leave the gravitation is not a pull. I'm sorry, gravitation is not a push, but a pull theory. But on that, I'm gonna just leave it there, because I think I have clearly shown what attraction looks like. The goal was to show you what attraction looks like. This is a force of repulsion. This is a force of repulsion. This is a force of attraction. In fact, I have if I can find it in time on the internet, I'm gonna look in my computer online real quick, because I wrote out a description of attraction and repulsion, and I'm going to read it to you, and then I'm going to show you the observation, and then we will go from there. So, attraction, as I have described it, is an observable force interaction that causes a potential mass, and it doesn't have to be a potential mass, that causes a potential to become kinetic with a momentum and geometric orientation that will vector toward the magnitudinal source. And then repulsion is an observable force interaction that causes a potential mass, doesn't have to be a potential mass, to become kinetic with a momentum and geometric orientation that vectors away from a magnitudinal force. All right, so I'm gonna wrap this up with this last bit of information. Okay, a force of attraction. That's the force of attraction. What do we have? We have a potential magnitude. This is the potential magnitude. This is the geometry between these is the vector. The vector is the motion and the acceleration. So if my statement is correct, what you should be able to see is the magnet that is stationary, because stationary equals potential in this experiment, move toward the magnet that is moving. The reason why the magnet that is moving has to be moving is because, as you can see, that there's no force interaction. I can't show you a force interaction without being a catalyst for a force interaction. That's the basis of the experiment. I'm going to use my hands to move the two magnets into an alignment where their magnitude will be great enough to create a vector that will show you what attraction looks like. And that's what I'm going to do when I slide this magnet toward the other one. It's going to show you a vector toward the potential mass, because my influence from my finger is only affecting this magnet. It's not affecting that magnet. The influence from the magnitude of influence from this magnet is going to affect this magnet, not the motion of my finger into the magnet, the actual force between them. The inverse rule states that the magnitude and the force between the two magnets is going to be inversely proportional to the distance between them. As this magnet gets closer to this magnet, the force between them will increase, and as it increases, the force will overcome the potential energy of this magnet and force it to become kinetic. That's what I'm going to show you, and this is going to be attraction. Now, we're going to flip this magnet 180 degrees, and I'm going to show you repulsion. Propulsion should work in the same direction, and it's always about orientation. It always comes down to orientation. Notice how as it gets close enough, it moves, it moves, it moves, it moves. This is what, if gravity was a push, understand, if gravity was a push, we would be thrown off the surface, because this is the center of the earth. This is the force, this is the magnitudinal force. This is the direction of the magnitudinal force. So, as you can see, there is no attraction. There is no moving toward the surface. This is what we see. This is what gravity is described as. So I'm gonna put this experiment to rest. I hope you enjoyed this presentation of my 2 cent. And as always, my name is Paul Emerson. And have a nice afternoon.